This is section 3.4 on velocity and other rates of change. Suppose we are given the position of a particle moving along a coordinate axis. The position is represented by the function 1/3 t to the third minus 9/2 t squared plus 14t plus 2. And s of t in this book represents the position of a particle or whatever object we're talking about. T will be measured in seconds, at least in this problem, and s of t, or the position, is going to be measured in meters. And for this example, we're going to look from 0 to 9 seconds. In the first example, we're going to be asked to find the average velocity over the interval 0 to 9. The average velocity is the change in the displacement over the change in time. Now I've written the equation up top here again. To find average velocity, it's the slope of the secant line from 0 seconds to 9 seconds, and that should be a straight line. So we're going to find the slope of the secant line, which is s of 9 minus s of 0 all over 9. And I've already typed it on the calculator to save a little bit of time. Let me bring it up. There's the function with 9 plugged in. If you plug 0 into the function, it's just going to be 2 because all of these variables will go away. So we have 6.5, which is what we get when we plug 9 into the function, plus 2 is 8.5, and then when we divide by 9, it ends up being 0.94. So the average velocity over the entire interval is, let's see what that value was again, 0.944. 0.944, and that's going to be meters per second. In our next slide, we are asked what is the velocity of the particle at t equals 3 seconds. So we're asked to find the velocity of the particle. Velocity, v of t, after a certain amount of time, is the derivative of the position. So if you have a function and you take the first derivative, you are finding the velocity. And in this case, it is, let's see, 3 times 1/3 is 1. And reduce the power by 1, so we have t squared. When we multiply 2 times 9/2, the 2's will cancel out, and we're left with 9t, and then 1 times 14 is plus 14. So there we have the velocity function. Now the question is, what is the velocity of the particle at t equals 3 seconds? Well, now we're going to evaluate this function at t, not x, t equals 3. So we have to plug 3 in. We get 3 squared minus 9 times 3, and then plus 14. So we have 9 minus 27 plus 14. Let's see, 9 and 14 would be 23. So we really have 23 minus 27, and that's equal to -4 meters, not feet. I was going to write feet. I believe we started with meters per second. Now speed is the absolute value of velocity. If someone asks you what was your speed getting here or arriving to school, you wouldn't say -7 miles per hour. You would say 7 miles per hour. Of course, that's a bad example. That'd be really slow, but let's say 35 miles per hour. You would never say a negative value for speed. So the speed equals absolute value of velocity. So the speed of the particle at t equals 3 seconds would just be 4 meters per second. In our next slide, it says the acceleration is the rate of change of velocity. Well, velocity is the rate of change of the position. So every time you take the derivative, you're finding the rate of change. So in this case, well, we start out with the original function, which is s of t, and then v of t, the velocity, equals the derivative of the position. And in that case, it was t squared minus 9t plus 14. Now, it says find the equation for acceleration. Acceleration is the derivative of velocity. It's the change in velocity. You know, if you press on the accelerator in your car, you're going to accelerate. Your velocity is going to change. That's acceleration. So the equation for acceleration is 2t minus 9 using the power rule. So here we have it. Acceleration, the formula, is 2t minus 9. This says what is the acceleration at t equals 3? So a of 3 equals 2 times 3 minus 9, which is 6 minus 9, which is negative 3 meters per second squared. That's the label for acceleration. This says what is the velocity when the acceleration is 0? So first we have to find out when the acceleration is 0. We set the acceleration formula equal to 0, 2t minus 9. So we have 9 equals 2t, so t equals 9 halves. So that's when the acceleration is 0, but the question really is, what is the velocity when the acceleration is 0? For the sake of time, I've already entered that into the calculator. So here it is. The formula for the velocity is t squared minus 9t plus 14, and I've plugged 9 halves into that. 9 halves is when the acceleration is 0, and they want to know what is the velocity when this happens. So we're going to use the formula for velocity, t squared minus 9t plus 14. And here's 9 halves plugged into that, and it turns out the acceleration is negative 6.25. So the acceleration is negative 6.25 meters per second squared. When velocity and acceleration have opposite signs, the particle is slowing down. When velocity and acceleration have the same signs, the particle is speeding up. I want you to picture throwing a pin or throwing anything straight up into the air. When you throw it up, acceleration is acting on that object, and the acceleration is down. So let's say negative, and the velocity is going positive up in the air. So the velocity is positive, the acceleration pulling down on it is negative, and that object, as you throw it up in the air, is going to slow down. When velocity is positive, acceleration is negative, or opposite signs just in general, the object is going to slow down. Now once that object reaches its highest point and starts coming down, then the velocity is negative and the acceleration is negative, and that means that as the pin or whatever you're throwing up comes down, it is going to speed up. So as you throw something up, it slows down, it comes down, it's going to speed up until it hits the ground, of course. So it goes back to when velocity and acceleration have the opposite signs, the particle is slowing down, and when velocity and acceleration have the same signs, the particle is speeding up. So let's talk about when this particle is slowing down and speeding up. Well, anytime the acceleration changes signs or the velocity changes signs, there's a possibility that it could be switching from slowing down to speeding up or vice versa. Now, this x to the third or t to the third graph is the position. The velocity is the parabola and the acceleration is the line. So let's look when the velocity, the parabola, is going to change signs. It happens right here at 2, because we can factor this into t minus 2 and t minus 7. So we have a 0 here at 7 as well. The acceleration changes signs at 9 halves, because if you set this equal to 0, you would add 9 and divide by 2, and so we're looking at 4.5. That's 9 halves right here. So we're looking at, let's see, here's one section, here's the second section, and here's the third and then the fourth section. So velocity or acceleration changes signs in one of these lines. So let's kind of keep track of acceleration and velocity here, acceleration and velocity in this region, and the same thing in the last two. The acceleration is the line and velocity is the parabola. So the velocity is positive up here and the acceleration is below the x-axis, it's negative. So here we're slowing down. Then when velocity changes to negative, the The acceleration is negative also, so they're both negative. Now the particle's actually speeding up. Here the velocity is negative, but the acceleration now has gone to a positive value. So acceleration is positive, velocity is negative. And in the last region, acceleration is positive, and now the velocity has crossed the x-axis again, and now it is positive as well. So they're both positive. So this particle is slowing down. Let's see, where? From, actually we're going to include 0 to 2. The particle is slowing down because acceleration and velocity have opposite signs. And there's another place where it's slowing down, and that is from 9/2 to 7. Acceleration and velocity have opposite signs. So 9/2 to 7. This particle is speeding up from, let's see, 2 to 9/2 because the signs are the same. 2 to 9/2. Union with, where else is it speeding up? It's speeding up from 7 to, well, we're stopping at 9. So 7 to 9, and we're going to include the 9. When is the particle moving to the right, and when is the particle moving to the left? We know a particle is either moving left or right based on the velocity. When the velocity is positive, we're going to say it's moving to the right, and when the velocity is negative, then we're going to say moving to the left. So, right. Let's see. The velocity is positive from 0 to 2. It goes negative to 7, and then it goes back to positive from 7 to 9. So this particle is moving right from 0 to 2, and then it's moving right again from 7 to 9. The particle is moving to the left from 2 to 7 because that's where the velocity is negative. So 2 to 7.